morning, everyone. Thank you very much for showing up, and thanks to the organizer for inviting me. So,
you have no expectations to your audience.
So today I'm going to talk about some kind of results we have, which are some of them already some years old, but they're still in the making. But one of kind of the line of research also led to another paper. I'm briefly flashing later, but this is basically work that started in a master thesis of a student, Alexander Eberharter, in Innsbruck with me. And then towards the end, we're also talking about a new idea how to extract velocities, so speed of light, basically, for CFTs. And that's work which we're discussing together with Lawrence and Frank. So I will start off with giving you kind of a very brief introduction why kind of critical phenomena and CFTs are kind of interesting, and then we'll discuss how one has obtained, for example, central charges and scaling dimensions in the past, and then I will basically show you how I think what is an alternative approach and what its strength might be. Yeah, I guess this is a very high-flying slide, so we're interested in quantum matter. We want to understand different phases of matter, but since different phases of matter are kind of separated by phase transitions, they have a particular interest to be studied. And so, just as a kind of a motivation, I guess if you work on phase diagrams and you try to chart what different kind of phases appear in the quantum many-body system as you change parameters, then we're kind of used to get colorful diagrams like that, where basically all the colored patches are a different phase. So here this is a frustrated spin model, also with chiral interactions, and so on. So there's a large chiral spin liquid region, and there's a magnetically ordered phase of one type, of another type, and of a third type, and here there's potentially spin liquid. And we're not going to discuss this model in detail, but here you can see there are at least 4 different or 5 different quantum phases, and I think actually a lot of the possible quantum phase transitions between them, I think, are not very well understood. And a similar thing is true for a strongly interacting model of spinless fermions here on a honeycomb lattice. And again, it's just to illustrate that just in a small range of some repulsion parameters, you can find the plethora of phases, and the nature of the phase transitions in many cases is not fully understood. So here the models are in 2+1 dimension, so I'm not heading there yet, but in that domain, I mean, some candidate phase transitions which are of course well understood are the Wilson-Fisher, like the Ising CFT or XY or Heisenberg. But if you go, for example, here to the interacting fermions, you get Gros-Neveu or Gros-Neveu-Yukawa type phase transitions, and in some spin, for example, this region here could potentially be a condensed matter realization of something like QED3, so which believed or could possibly be a massless conformal field theory in the infrared, so in the long distance level. So there's plenty of things to be understood in 2+1 dimension, but let's first try to understand how much or how accurate we can do things in one dimension. And so in one dimension, conformal field theory is a very kind of rich topic, and I think there are also some experts in the room, so I will not kind of make an entire lecture about it. But there are a few things which are kind of interesting. So in 1+1 dimension, the conformal group is actually much larger than it is in other space-time dimension, and that kind of brings the fact that it has a lot of mathematical structure, and conformal field theories in 1+1 dimension can be understood in a lot of details. I think there are still open questions, but compared to higher dimensions where one is much more limited in kind of precise or exact understanding, in 1+1 one has already achieved a lot. That's basically what I said. And so, as you all know, kind of in statistical mechanics or in condensed matter system, at quantum critical points, these CFTs are expected to describe many of these points. I mean, not all of them. There are quantum critical points which are not described by a CFT, but it turns out that many theories or kind of critical points of interest are described by a CFT. Here this just for the newcomers, for example, in 1+1 there is the IC CFT, which is called very prominent. There are multi-critical IC models, there are Q-state POTS model, or 3-state as the simplest instance. And the Luttinger liquid is actually also a CFT with a kind of with a variable exponent, or kind of a line, a class of, or a family of CFT, and also based on models are important. And we actually here, as you can realize, several of these theories already popped up basically here in the context of this workshop. And then in the title I said something about CFT data. So the CFT data come in different disguise. So the central charge is a very important quantity which characterizes in some cases uniquely the conformal field theory, but there are also some values for the central charge where a larger number of possible CFTs are allowed, and then you have to further characterize them. And then the operator content is important. So these are kind of the fields and their scaling dimensions, which are allowed in a certain series. That's also part of the conformal data. Then there are OPE, operator products, expansion coefficients, and also there's a certain boundary condition dependence. And so here there are some kind of standard references in case you're new and you want to jump into this. Okay. Yeah, so as I basically mentioned, if you dive a bit deeper into the relation between, say, field theories and statistical mechanics, you actually realize that, this has been understood a while ago, no? But that critical exponents which we measure, they're actually often closely, they can be mapped or they derive from properties of the scaling fields, and scaling fields, they have a scaling dimension, and so this is basically the eigenvalue of a field under a renormalization, a rescaling transformation, but these eigenvalues actually kind of determine a lot of the critical exponents. And then another way to actually measure them, which is perhaps more kind of more widely known, is that actually if you calculate a two-point correlation function, then the spatial or temporal decay of those is usually governed by here 2 times the scaling dimension of these are the same type of fields. And to make things more concrete, I mean, now this looks like a field theory expression, but in the end, if you study something like an Ising model, then objects like this OI can be something like a local spin, like a sigma C operator, sigma C correlation function as a function of distance, or it can also be some bond energy, so like a product of sigma C on one bond and another bond far away. And if you look at the spatial dependence, these decay as a power law at the critical point, and that power law is actually directly related to the scaling dimension of the operator, which basically you're cutting to when with your lattice objects. Yeah, and so it's interesting and obviously important to know kind of the set of fields and scaling dimensions in your theory, and the question is how we can find those. And so this is not the main topic of the talk, but something which I always find fascinating is actually that if you study energy spectra, for example, of one-dimensional systems, then so here, for example, this is a spectrum of a transverse field Ising model on a finite system of only 16 sites, and this is a slightly more complicated kind of anion chain. And then actually, it turns out because of some insightful mapping between the planar R2 space-time onto the cylinder. This is a cylinder, so this is like a compact dimension S1 and then an extended one R. You can actually understand that basically the spectrum of operators actually maps onto the Hamiltonian spectrum of a 1+1 dimensional quantum many-body system. And so what you actually observe here, the finite size spectrum, is not just a lot of numbers, but actually, if you look carefully, then the relative position of these levels with different quantum number under the Z2 symmetry, they actually arrange precisely like the conformal tower of the Ising CFT. And I think this is a very beautiful example of how you, when doing numerics, I mean, you can actually stumble over algebraic structures which are very profound and which, for example, here are basically are consequences of, say, the representation theory of these Wehrmann modules of the Virasoro algebra. And so here, this is done just using exact normalization. We will see later that actually similar spectra can in the meantime also be obtained in finite size DMRG by looking at the spectrum of the DMRG superblock, and Natalia and Frederick had a paper on that, revealing this property. And also there has been some interesting work recently by Guifre Vidal's group, where they were doing periodic boundary condition uniform matrix product states, and they were able to similarly extract the low energy spectrum using iMPS techniques. So these spectra are now also already available or accessible using tensor network techniques. But of course, something I guess in the tensor network community is extremely well known is that a certain quantity of interest in a conformal filter is the central charge. And I guess what many of you, including me, are doing a lot is that if we're starting using DMRG here in a finite size setup, a system of a certain length, capital L here, and then look at the subsystem of a certain size small l, then Calabrese and Carney worked out this famous formula where the entanglement entropy, the von Neumann entropy of a subsystem controlled by this small l in the system size of capital L has this nice formula. So if you, here the specific model we're studying is a Bose-Hubbard model where if you change the interactions going from a quasi-superfluid, which is a Latinger liquid, so conformal field theory, to a gap phase. And so here you can see the area law at work, whereas here this kind of form is precisely this Calabrese-Carty formula. And if you fit this formula to these numerical data, then you get relatively precise central charges out, which up to a few parts in 1,000 are close to 1, which is the expected value. And this is just plotting the same data differently, where basically one combines this argument on the x-axis, and then you find basically things which are linear, and then so then the fit is easier to see how good it is. So this is already pretty accurate, so that's good. And another thing which where you can see conformal data in matrix product state or DMRG is actually in the entanglement spectrum. So that's something I came across some time ago. And so to stick with the Bose-Hubbard model, so we're sitting here in a regime where the interaction is relatively small. So it's in the superfluid or this Latinger liquid phase. And since we're in a finite size system and we're using particle number conservation on the entire system, then the reduced density matrices actually are also block diagonal. And so I can basically plot the entanglement spectrum, so meaning minus the logarithm of the eigenvalues of the reduced density matrix. I can label them as a function of the deviation of the particle number sector with respect to the nominal kind of unit filling case. And so if you plot this entanglement spectrum with this way here, that's just kind of the raw entanglement spectrum for a half-half partition in a system size of a few hundred sites or so, then you get this structure. And if you actually flatten it out, which means you remove this parabola, which you have here, basically you shift all the vertical lines down to 0, and then you rescale everything basically to this distance, and you actually see that curiously there's a kind of interesting structure here. So it actually seems, perhaps you have seen it, realized it before, but there's actually a second parabola here which is actually shifted with a constant shift with respect to the first one. So that basically translates into these data points lying on the horizontal line of value of Z1. And there's another one here which actually now is twofold degenerate, which is at offset 2. The number is increasing, and if you start to look at the counting, then it's 1, 1, 2, 3, 5, 7, and so that's also something people know from the fraction quantum Hall effect. So some edge states actually have the same counting. And so where we're basically heading is that this entanglement spectrum is not just some combinatorical curiosity of the Bose-Hubbard model, but what you actually observe here is actually also a conformal tower of basically the Latinger liquid or of the compact boson CFT if you want. And this is not just kind of a nice result which tells us that CFT structure is also showing up in the entanglement spectrum. This actually also has practical value, because if you go back and you ask yourself, kind of the effect which you have removed by flattening it out, what is kind of the curvature of this parabola in units of this spacing, then basically these relative values, they actually encode, if you want, the compactification radius of your boson, or this one free parameter which you have in a Luttinger liquid. And so, so here I then apply this to a number of models, an XXC spin chain in zero field, but as a function of the anisotropy in the Luttinger liquid region, or here it's a spin 1 Heisenberg chain in a magnetic field, where basically the entire field range from 0 up to close to saturation is a Luttinger liquid, and here it's the magnetized phase of the spin 1 Heisenberg chain, and basically in all of these cases, and these results are the ones from the entanglement spectrum. You can estimate easily the kind of the Luttinger liquid parameter or the correlation exponent of some correlations, and here this also I think is a very cheap and very nice way to get the non-trivial dependence of the Luttinger liquid parameter in the Heisenberg chain in a magnetic field. Yeah, and this is kind of yet another example. This is the three-state Potts model. This is just to say that there's a lot of structure in it, but at the end of the day, if you look carefully at the degeneracy, which are intrinsic in the entanglement spectrum in the symmetric phase, then you can actually see that the spectrum which you obtain is a subset of all the possible Virasoro towers of the three-state Potts CFT. So this is like one copy of this one, 2 copies of that one, and another copy of that tower which have certain scaling dimensions. And if you combine all them, then basically you obtain this spectrum. And so this is not just kind of some empirical observation. Actually, there's also some kind of a picture which later Bonnie and Carty kind of worked out, that basically what we observe in the entanglement spectrum is actually also related to the operator content of the partition function of the C on the strip. In this particular case, with 3 boundary conditions, and if you change the boundary conditions by, for example, changing the physical boundary conditions of your chain, which you're simulating in EMRG, then you can actually change the operator content of the entanglement spectrum. Therefore, check for consistency whether your theory really looks like a CFT. Okay, and so this was kind of a short overview of some, okay, it's a bit biased by my own work, but things where, like with in finite size EMRG, you have access to some CFT data, and now we basically want to explore whether you can also get accurate data with iMPS, but of course here work has been done before. And so now, for those who are not experts, which are probably no one here, but the idea is basically, you have to differentiate if you work in a finite system, then and you work at sufficiently large bond dimension, then actually a lot of the results which we get using DMRG are basically controlled by the system size, and at least in conformal field theory there's a very good understanding of what happens to conformal field theory if you put it in finite volume. So a lot of analytical work has been done on that, and therefore kind of DMRG is then a tool where in an unknown model you can try to figure out whether some of these predictions for certain CFTs are realized. Now in the iMPS setup is different, because there's formally no system size, so kind of formally our system is infinitely long, but still there's kind of some effective length scale, and that length scale is the finite correlation length. We kind of know happens there, because with the finite bond dimension which we're using in practice, it's not possible to exactly represent the CFT wave function, so we necessarily introduce a cutoff. But that cutoff, due to the finite bond dimension, is precisely the origin of this finite correlation length. But what will be a recurrent theme, basically, or a side note of the rest of my talk, is that basically the precise, say, CFT picture between what is the effect of the finite bond dimension and what is the precise CFT picture, which describes the situation where the finite bond dimension induces a finite correlation length. I think there's some understanding lacking there, and so we have to somehow work around this at least current lack of knowledge. So it's not a complete lack of knowledge, but I think the details are not understood, and this leads to some small gaps in, say, precision or understanding. And so what we then start to do is basically look at how kind of entanglement scaling has been done in the past, and there's some very nice and influential work by Luca and Frank Holman and others more than 15 years ago or so, where they basically observed and also to some extent explained and understood what's happening if you put this finite bond dimension in an iMPS setup. And so kind of an interesting formula is this relation between the bond dimension d, which you put in your MPS, which you then optimize, and the correlation length which you obtain. And so using some ideas on the asymptotic scaling of the entanglement spectrum with kind of the large tail of the entanglement spectrum, one can actually relate this exponent kappa in the end to the central charge, which appears here in this formula. So there's a relation between this exponent kappa, which governs how quickly the correlation length grows if you increase the bond dimension, is in the end governed here by the central charge. And so I'm not questioning this formula, but as you can see, I think this is the correct first order or high order kind of result, but I think we cannot systematically refine it, and so I think there's work to be done there. But if you stick to that, I mean, if you basically then use this correlation length, which is induced by the bond dimension, you can somehow plug them into Calabrese Carty-like formulas for infinite, and replace kind of the system size or the interval length by this correlation length psi, and then you get formulas like that. And so either you see that the entanglement entropy, it has to be finite because of the finite bond dimension, but it scales as c over 6 log psi, or c times kappa over 6 log mu of the bond dimension. And so this is a very popular way to estimate the central charge, and it's also reasonably accurate in many cases. So the point I won't make, because I have an alternative, is that once you really look into very detail how these curves look like, so this is now, one of them is actually the entropy as a function of the bond dimension. These are the black thing. And what we did here, I think, is that we basically for all bond dimensions between 42 or something and 64, we optimized an MPS for the Ising model at its critical point, and obtained basically a pair of bond dimension and entropy or correlation length and entropy, and we plot this line. And so typically you would then make a few points, usually doubling the precision, doubling, say, the bond dimension, and then measure the correlation length and make fits. And of course, this is already very accurate. I think this is often accurate to a percent level, or even 1 part in 1,000 or so. What you get out. But I mean, I'm not the first one to observe, I guess, but if you look very carefully, you actually can see there is quite a bit of residual oscillation, or some structure which at least I don't understand, and they're actually there in both of the and I think if you really want to amplify the effect, what I do here is basically I make this fit, and then I remove the fit, and I just look at the residual oscillations around the fit, and then you can see that there's still quite a bit of noise. But since there are many data points in the end, the fit is really quite stable, and here it's actually hard to see, but here there is the expected kind of slope, or kind of the expected value of the entanglement of the central charge for both cases, and the differences are really small. So I'm not saying that this is something super kind of inaccurate, but still there are oscillations on top, and I think we don't really understand, or we don't have a quantitative explanation of those. I think that's fair to say. So therefore, I felt, at least in some cases, when you want to somehow have a program or an understanding where you can do systematic improvements, like if for some reason you're obsessed or fascinating in calculating the central charge of the Ising model to more than 2-3 digits, I mean, how would you proceed? And so what I'm saying here with this approach, I think this is currently not feasible, because the theoretical understanding of what was the correction beyond what we observe is not there. We cannot systematically improve it beyond the very good quality we have, but we cannot systematically improve it.
So Andreas, how should I interpret the y-axis on the right plot? These are just shifted for clarity. They should be centered around 0, or like you subtract the fit from the actual data, and then it oscillates.
Okay, now I mean, I think I realized just I was wrong. So what I actually did was building center differences about the data points. So they amplify really the kinks in the. And so these are the central differences, but they are just a few points and they do not include the full field. So the theoretical line would then be like
okay, like this.
Yeah. So the central differences are basically just amplifying the oscillation because they just involve 2 points where there's a big, the slope is fluctuating quite a bit between adjacent points. But I mean, you see that there is a bit of course, a kind of a bad intent because I want to amplify an effect. It's not that this is a major drama, but I'm just pointing out there is noise in the data which we don't understand. Okay, and so at least for some of these models, I think we have a way around which comes a bit in a different flavor. And so basically we're kind of evading the problem. As I said, I think the space-time picture for what is actually kind of the perturbed CFT once we have a finite bond dimension, I think is not understood in full detail. But there are other regimes where I think we understand what's going on, and so that understanding is, for example, what happens in the vicinity of a CFT if you perturb it with a relevant perturbation. So this is kind of conformal perturbation theory. This is a well understood topic in 1+1D, and for example, there's conformal truncation methods which operate with ideas like that. So this is nothing new, but perhaps it has not been used in the context of MPS the same way. And so the idea is basically we add a relevant perturbation to our CFT. So we on purpose go off critical, and we do this with a perturbation we understand, or we can also measure its scaling dimension after all, but we have to put the relevant perturbation. And so, kind of just like conceptually, right, there's a CFT Hamiltonian, and now we have a coupling constant lambda, and then we add basically a space integral of a relevant field phi, and so the dependence on lambda, this additional coupling will play an important role. And so the scaling dimension of this field, which we add, should be as relevant as possible. That's what we explored, and relevance here means in 1+1 that the scaling dimension is less than 2. And according to well-known kind of RG formula, like if you perturb not even a CFT but a fixed point, then basically you would expect that there is a correlation length emerging in the vicinity of that critical point, which actually depends in this way on the scaling dimension of the relevant perturbation and on the coupling constant which you apply. And this is now also a way to actually regulate the entanglement entropy, because the entanglement entropy now becomes finite because we have tuned the CFT into the massive phase, so in the gap phase, with the perturbation, and not because of the bond dimension. So somehow we're replacing the mechanism which gives rise to a finite entanglement entropy by a relevant perturbation, which is kind of a physically well understood kind of idea or mechanism, and we evade the finite entanglement scaling aspect directly. So to some extent we try to take the bond dimension out of the problem. Now there are some formulas, but so the first ingredient is basically that we apply relevant perturbation, and another one is a bit technical, but the practitioners perhaps also know that, is that the correlation length, which you actually extract from an MPS, actually has a very kind of slow dependence on the bond dimension D. And so what I mean by that is that even if you're kind of off critical and the system should have a gap and a finite correlation length, actually turns out that some quantities, like for example the entanglement entropy, there are converged to much higher precision as a function of the bond dimension for that point away from criticality than for example the correlation length. The correlation length takes much longer to converge, and also there have been papers addressing this with a kind of an interesting extrapolation schemes based on gaps in the transfer matrix, but still you have to use tools like that, otherwise just the raw correlation length is actually has a lot of tricks with the bond dimension. That's kind of an empirical fact. Probably also has to do with the way the correlation length is defined, but this is something where basically the correlation length still has a sizable bond dimension dependence, and so we want to get rid of that. And so what we use basically that we use this formula, which by now is well established, and we actually replace basically occurrence of a correlation length by basically by this formula. So if we invert it, we're basically saying that the correlation length is actually now represented by the exponential of here 6 over c, the entropy minus the entropy offset. So I'm just inverting this formula. But this has an interesting appeal, because now I can rewrite for example, simple formulas like the if you want that a local, so a vacuum expectation value of a field is basically would be something like 1 over the correlation length to the scaling dimension, and if you replace that in terms of entropy, you get this exponential dependence of this vacuum expectation value on the entropy, and there's a prefactor which involves the scaling dimension delta phi and the central charge. And also lambda itself, which is the control parameter which we are not measuring but imposing, it actually also has a relation like that between these. So I think here actually this scaling dimension delta theta is actually the one of the perturbation which we are implying, whereas this can be a general operator which we are measuring.
Question.
Yes?
The expectation value should be well defined in the thermodynamic limit, right?
Yeah, so here is the expectation value kind of at finite lambda which we're measuring.
Because the right-hand side seems to be system dependent, right? Or dimension dependent. This means if psi increases, then S increases.
Sorry, which one? What do you want to read? This one or that one?
On the bottom, the right-hand side depends on the psi.
How that?
Because of the S. The S is growing as the psi is growing, as the bond dimension is growing.
This is off critical.
Yeah, so the true correlation length or the true value of S is actually controlled by the value of lambda we said. So if lambda is finite, and if bond dimension is set to infinity, S is finite and psi is also finite.
Because it's off critical.
Yeah, because that's the effect of lambda. So we're going on purpose of criticality. But the idea in the end is actually to reduce lambda, to go back to criticality and look what's happening in the vicinity. But that's I mean, in conformal perturbation theory, it's kind of a well-accepted idea that actually the vicinity of the critical point is actually governed by properties of the critical point. So it's not that vast surprises can happen in the vicinity of a CFT, but if you perturb it with a relevant operator, it's well understood what happens in the vicinity. And so what we're doing is basically, let's watch in the vicinity where our setup, I try to convince you, is more accurate, and then learn something about what's actually happening at lambda equals 0, where we're not going, but we're getting very close as much as we can afford. Yes?
On the right-hand side, I mean, say, most quantities are known, but S0 is still to be determined, right? I mean, S you are measuring from your data, but S0 is non-universal.
But we will see basically what we're going to look at is then we're taking logs on the left side, and then we're taking derivatives, and then S0 is just an offset which doesn't matter. Yeah, but something I would like to mention is that something which plays a role later to determine the central charge is that actually you can define something like an excess energy. So here I'm calling it like a vacuum expectation value of the Hamiltonian, and this is a bit like an analogy to the CFT there, the stress energy tensor. You can also measure its expectation value, and if you're at the CFT, it's basically 0, but if you're going away from the CFT, it requires a finite value. And so what we're basically doing here is that what this is basically, it's the CFT Hamiltonian, so the energy of the CFT Hamiltonian evaluated in the MPS which we obtain from the off-critical optimization. And so by the variational principle, like the wave function we obtain as a ground state away from criticality, it cannot be lower in energy variationally than the ground state at criticality. And so this energy difference, that's basically what we mean by that, is actually also controlled by a critical exponent, and since the stress energy tensor has a fixed scaling dimension of 2, basically there's no uncertainty here on what the scaling dimension is, but we basically take this formula and replace that one by 2, because that's the kind of the guaranteed scaling dimension of the stress energy tensor, and then we get this formula. And that's kind of important, because now the only thing unknown is basically the central charge, so we can actually use this measurement to determine the central charge. So this is kind of important.
I have a question. Yeah.
Yes.
So you have the scaling relationship that relates S and Xi, but isn't that only true, strictly speaking, at the critical points? Like the relation you start with at the inverse. C is 0.
Yeah, but I think basic Carty also, I don't know to what level of rigor, but this formula also holds slightly off criticality. I mean, they have.
So what is the distance over which this can be? I mean, it's just empirical, I guess.
Yeah, I guess so. Yeah.
But typically, you don't know.
Sorry?
So from microscopic model, you don't know it's tilde.
So if
You mean the reference and vacuum energy at criticality?
So the stress energy tensor. No, you don't.
I mean, what we do in practice is reach a microscopic Hamiltonian, which defines our model, and if we know where the critical point is, then we evaluate the Hamiltonian at the parameter choice, which is the critical point.
So then you expect that then you would also have the descendant of the T00, right? So it won't be really T00. So that operates, that maybe.
You mean there are higher order corrections or something? Yeah, okay, but this is just leading order. Yeah, and so now basically I have already been asked, but then what we're doing is that we then take the log, for example, here of this excess energy, or we take the logarithm of some local magnetization which you measure, or we take the logarithm of lambda, and then if you take the log on the other side, obviously the exponential goes away, and you obtain linear relations. Then, for example, then if you take kind of these logarithmic derivatives, you get formulas which, for example, here you get -12/c. If you measure the excess energy as a function of lambda, and then you take the derivative with respect to the entropy, so not with respect to lambda, but with respect to entropy, then you actually get nice results. Okay, this is all kind of paperwork, so let's see how that actually works in practice, whether this is any good. And so, just kind of to set the stage, so we're in the first example, we're basically working with the transverse field Ising model. So this is sigma c part and the transfer field. So that part alone is already at its critical point, as you might know. And then we basically add perturbations. And so this p part contains either two terms. Either we detune the transverse field here with the lambda x. And so in the Ising model, in the 2D classical Ising model, this means like changing the temperature, either going to the paramagnetic phase above for one side, or going in the symmetry broken phase below. But if there's no lambda x, just a lambda c, basically, then we're adding a uniform magnetic field. And just for kind of to remind you, so if this is kind of the critical point, the quantum critical point, or the thermal critical point in the 2D classical Ising model, there are two RT relevant directions. Either you add a magnetic field, then you go gapped, or either way immediately, and this is all gapped and paramagnetic here. However, if you have no magnetic field, then you go below the critical temperature or the critical transverse field, then you end up with a spontaneous symmetry broken phase. The two direction here, this is kind of the thermal one, and in field theory language, or let's say here with the sigma, that's basically the perturbation to the magnetic field. That's very relevant. It has a scaling dimension of 1/8. And the other one, if you change detune the transverse field, this is like the thermal perturbation, and here the operator in the CFT has a scale dimension of 1. And so now let's show some first examples. So now what I'm showing, so I'm looking at the transverse field Ising model. I'm changing, adding a longitudinal magnetic field, so a sigma z field in the language of before. And here I'm using a very small bond dimension chi=4. And what I'm showing here now is I'm calculating what I call this running central charge, this C of S, which is defined as this kind of the derivative of the entropy of the excess energy with respect to the entropy, but in this log form I showed before. And the different data points is basically we're using kind of a logarithmic grids of lambda values. And so here lambda is very large, so we're basically in the product state imposed by the longitudinal magnetic field. Entropy is very small. That's why I start off here, and these points are, as I said. And so basically what you can see, this curve start to rise here, start to bend over, and then it drifts away to larger values. Okay, and then if we do chi=8, we see that kind of for large perturbations, these curves lie on top of each other, and now the green curves continue somewhat further than the red one, and then it also starts to fork off and go higher up. And as you can imagine, if you double chi again and again, then you get the curve which actually gets closer and closer to this curve 1/2. And here you see also an indication what these values of lambda are, which correspond to these different points. So if you want to zoom in, you can see that, I think what this was on dimension 256, you already see that here at the last point, we get basically a precision already which is like close up to the 4th digits, which I think is quite a bit better than what was obtained in the finite entanglement scaling. And we can also do that kind of even more quantitative. So this is kind of the same plot, but here I think the bond dimension goes up to 768. And here basically I'm plotting the difference of the running central charge with respect to the expected value of a half. And here you can see that we're basically, for the largest bond dimension, we're getting close to the difference, which is of the order of 10 to the minus 4. So I think that's quite precise. And then what we can then also do is measuring the scale dimension of the field, which we actually introduces the perturbation. And so that's basically measuring the longitudinal magnetization as a function of basically entropy, so that's just like, and then taking the corresponding logarithmic derivative in respect to the entropy, so this curve here, so it shoots up and then converges to the expected value of 1/8. And again, if you plot the difference, then here you get very precise. So here, like the largest system size is now going below 10 to the minus 7. So I think this is extremely precise for a scaling dimension using iMPS.
Why does it go away?
Sorry?
Why does it go away at the perturbation?
Is here?
Yeah.
That's the finite bond dimension effect. Once you, things are kind of under control and are kind of controlled really by the perturbation, by the relevant perturbation in this regime where bond dimension does not play a role. But if your correlation length, or if you're exhausting your bond dimension physically, if the correlation length starts becoming limited by the bond dimension and not by the perturbation lambda, then the results start to drift off.
But still the effective effect is that you have a correlation length and an entropy, right? Where in your formula, where were you assuming that correlation length was coming from?
Nowhere, but I think also in the finite entanglement, it's also not. I mean, there's no explanation. I mean, one.
I don't want to stop you. Maybe we can discuss later. Yes.
Okay.
You did obtain it from distant correlations, right?
Oh, pardon me?
Is it from spin-spin correlation?
No, this is a one-point function. So I just measure sigma c basically. I measure how much sigma c is induced by my perturbation, which is a sigma c magnetic field. So I mean, these values are actually quite large, but then if I take this logarithmic derivative, I get this scaling dimension.
Super easy.
If you take the derivative with respect to S, right?
Yes.
So the S data itself needs to be very accurate.
So that's my observation. S is very accurate. Like at the same lambda, that's a bit the point I mentioned about the correlation length. At a certain value of alpha, if I track what's happening, what is the precision of observables, then like the local magnetization, also the entropy, as a function of bond dimension for a fixed lambda, converge to much more digits at a certain bond dimension, and the correlation length, for example, would actually drift much longer. I mean, this is an observation which has been made before, but here for my scheme it makes a difference. So I actually switch to the entropy because the entropy is much more precise at the same bond dimension, so that these results are much more precise. And if I would reframe everything in terms of correlation length, which on paper would be equivalent, but in practice it would give much worse results because the correlation length would still drift, so all these curves would have a much more pronounced drift with one dimension than what we see now. Okay, so I think now I have to accelerate a bit, but so basically now we extend the story to the POTS model, and here just kind of why are the POTS model interesting beyond the fact that they are kind of the next more complicated models after the IC model. But if you study the POTS model, the classical ones, but also the 1+1 Hamiltonian versions which we're studying, it actually is well known that kind of POTS states 2, 3, and 4 are still CFTs, and it's known what CFTs they are. But if you go with Q beyond 4, so 5, in the lattice model, you can, the first model you can implement with 5. And while this is interesting, I mean, these models are well understood, but what is interesting is actually that they become first order for Q larger than 4. But to some extent, Q equals 5 looks very much like critical, at least through some lenses. For example, here in this paper, I think Naoki is also here, Noel and Anders were involved, some collaborators. They studied kind of using Monte Carlo, this model Q equals 5 also, but it's analytically known what the correlation length is, and I think this is a striking number because Q equals 5 is first order, which means at the transition, the correlation length does not diverge, but at q equals 5, the remnant correlation length is still 2,500 lattice spacing. So I think by many standards, this is a huge correlation length, and so that might be a challenge, or is a challenge in Monte Carlo, for example, to actually reach unambiguous evidence that the transition is first order, because the common law is that you have to study system sizes which are at least comparable to this correlation length in order to decide. Yeah, so we're starting quantum versions of this. So, and here I just want to, I'm just showing now the same quantity, which is the running central charge for the kind of Q equals 2, which actually is just the Ising model in disguise. Then we look at the Q equals 3 POTS model and Q equals 4, and the curves which we obtain until we exhaust the bond dimension, the compute power we have at our disposal, they clearly go towards curves. I mean, usually Q equals 2 and 3, they saturate, and the values are in agreement with what we expect. And Q equals 4, it actually has a marginal operator, so there's a logarithm here, the conversion is not as nice, but at least it's still kind of going further up, and it's likely converging to C equals 1 as expected. But now I think what is an interesting result is that if we do Q equals 5 with the same kind of scheme, then actually there is an intermediate maximum in our running central charge, and then it starts to drift, and that maximum is in a region where there's no question that our scheme is controlled and converged. And so we see actually using through this lens of perturbing the POTS model with kind of the equivalent of a magnetic field, actually it's very clear that Q equals 5 is very distinct from these other continuous cases. And so what we learn basically through this is that adding this relevant perturbation reveals the first order nature of these transitions much more clearly than, for example, doing simulations without this magnetic field perturbation.
And Andreas, this with the bond dimension, would you also see that clearly?
Sorry?
With bond dimension, would you also see that clearly?
What do you mean?
With the standard finite entanglement scale? Or not?
I have not done this very precise exercise, but it's true that Ingen He also had a paper earlier where he looked at fits of the entanglement entropy for different system sizes, and he saw big drifts, so actually also for Q equals 5. So I think in the entanglement entropy, also in other diagnostics, you can see that something's odd about Q equals 5. But let me perhaps skip this, but I just want to highlight that because of this observation we had in these results, we basically went back and basically did iMPS just in the plain lambda observable formulation, because that one can also be translated to the basically to quantum Monte Carlo, and then using these ideas of actually adding relevant perturbations, we also did a study to address the 2+1 dimensional JQ model, which is a candidate for deconfined criticality, and actually using our QMC implementation, using these ideas of adding relevant perturbation, we actually see, in our opinion, clear evidence that the JQ model, at least on the square lattice without any further terms, is actually also weakly first order. And so that's a paper which is out, but that's not the main topic of my presentation. And then, to at least conclude that part now, what we can now also do, and this running central charge is an interesting experiment on the spin S Heisenberg chains. And so you might know, okay, so you might know that the spin S Heisenberg chain is like the model system to study Haldane's conjecture, so that there's a difference between half-integer and integer spin chains. And also there is the idea of asymptotic freedom, which means that kind of in ultraviolet, these spin chains should actually become the same as two massless bosons. And I think there have been prior papers which try to somehow show that, but it was a bit in a hidden way. But what is now nice is that we can study this running central charge using our scheme, and we start first with the spin 1/2 chain. So this overshoots and then goes down to C equals 1, like the Westomin-Witten theory, which is expected. But basically all the other spin chains then have a transient region where their effective central charge is somewhat above 2. And then spin 1 actually starts to break down because it's capped, that's no surprise. And then the other ones actually start to level off and approach C equals 2 at intermediate scales, because entropy is also something like scale. and then, for example, spin 3.5 at some point starts to die if also go to c equals 1 as expected, spin 2 forks off and so on, and the other one continue, and we cannot simulate them, but we expect spin 5.5 to later also cross down to 1 and so on. But what is really nice is here that is this intermediate plateau where basically you see kind of the asymptotic freedom result, that this theory basically that intermediate scale is free and corresponds to like 2 massless bosons, and only in the infrared you either fork off to West-Witten level 1 for the half integers, or you go gapped for the integer ones, and you can actually nicely see that behavior here basically as a function of scale. And so I would also have results here, which I skipped now, but you can ask me in the lunch break, and I conclude here. And thank you for your attention.